Hi, students. This is going to be the first section of Chapter 7. We're going to talk about exponential functions and their graphs. Chapter 7 covers exponential and logarithmic functions, their graphs, and solving equations related to exponential and logarithmic functions. So let's get started with 7.1. Here we're going to talk about exponential functions and their graphs, and then solving very basic exponential functions using the one-to-one property. So exponential functions really come in two forms. One is where the base is greater than 1, and those grow exponentially, and the other is where the base is between 1 and 0, and those decay exponentially. So let's take a look at what an exponential function is. An exponential function is of the form f of x is equal to some base, which is just some number, with the variable x in the exponent. So whenever your variable is in the exponent, that's what we call an exponential function, okay? If, again, our base is greater than 1, then it exponentially grows as x increases. But if our base is smaller than 1, yet still greater than 0, if our base is smaller than 1, we're going to exponentially decay, because you can imagine when you multiply repeatedly by a number less than 1, you keep getting smaller and smaller. Exponential functions that we are going to cover are not do not include negative bases. Having a negative base makes things very confusing because, as you know, multiplying negative numbers, if you multiply them an even number of times, you result as a positive number. If you multiply a negative number an odd number of times, you get a negative number. So we don't define exponential functions for negative bases because we would be alternating between positive and negative numbers, and it would get very weird. So let me define some parameters for exponential functions. So some equation y equals b to the x is an exponential function if b is a positive number other than 1. If b is 1, it's not very interesting. Exponential functions have variables as their exponents. And here are some general characteristics of exponential functions. The domain, meaning the x values you can plug in, is going to be the set of real numbers. The range, though, is just going to be positive real numbers. And now this is assuming that we have no no shifts. If we have any shifts, then it could change our range, right? If our base is bigger than 1, our graph increases from left to right, and it's going to intersect the y-axis at 0, 1. As you can imagine with this equation, y equals b to the x, whenever x is 0, since anything to the 0 power is 1, it doesn't matter what our base is, it will intersect the axis at 0, 1. That's the y-axis, okay? As x gets more negative, the negative x-axis is the horizontal asymptote of the graph. And this, of course, is assuming we don't have any vertical shifts. Now, in the second case, when our base b is some number between 0 and 1, say 1/2, then the graph decreases from left to right, but it still intersects the y-axis at 0, 1. As x increases, the positive x-axis is our horizontal asymptote. So in both of these cases, assuming we are not adding in any vertical shifts, we do not cross the x-axis, okay? And that's because in the equation y equals b to the x, there is no value of x that will make y 0. Here is kind of a summary of the different ways that we can shift these graphs. They are pretty similar. The x and y shifts are just like x and y shifts we have seen before. The reflecting and the shrinking are also very similar. If you want to pause this or come back to this slide at some time, you are welcome to do that. I'm not going to read the whole thing. Let's instead just take a look at some of these examples so that you can see how our function works. All right, so here we are on this first example, and let me try to make it so you can see better. This first example is 3 to the negative x. As you can see, because x is negative, we have flipped ourselves around so that we are actually decreasing. Keep in mind, this function is actually the exact same thing as if we were to say 1/3 to the positive x. Okay. Some important points to notice. We still cross the axis, the y-axis at x is 0, 1. And when x is 1, we are at 1/3. Okay. So those are kind of 2 points you want to know. What happens when x is 0? When x is 0, our function is just going to be equal to 1. And when x is 1, our function is going to be equal to the base. Okay. Now we can do a couple other things. We can have a graph that multiplies by 3. So here, all our y coordinates are going to be multiplied by 3. So from our regular 0, 1 position and our 1, 5 position, because our base here is 5, if we multiply this by 3, it just multiplies all our y coordinates by 3. If we multiply our x, let's say by 2, it's going to do a very similar thing. It's just going to steepen everything by 2. Okay. Now we can also do some shifting. Maybe let me show you a very simple. If our function is 1/2 to the x, let's get these guys. If a function is 1/2 to the x, it is a decreasing function at 1 and 1/2. But if we add this plus 3, it is going to shift us to the left 3 units, right? Because we know anytime we add something to x, it's like it's x minus h. Okay, we're shifting to the left by 3. If we were to subtract it, we would be shifting to the right by 3. Right? And then we have our vertical shifts. And let's get rid of this. Let's just say we have 2 to the x. So our 2 to the x, we have our point at 0, 1. We have our point at 1, 2. We can shift this vertically by adding or subtracting. And you notice that we shift up exactly 4 by adding this plus 4 right here. So our vertical shifts, our horizontal shifts all do the same thing. If we want to flip over the x-axis, we do that just like we did before, okay? If we want to shift over the y-axis, we can make our exponent negative, but keep in mind that is the same thing as making the base a fraction, okay? So these two are the same. All right, so you've got your vertical shifts, our horizontal shifts, and then see the difference if we have a positive base, a base greater than 1, we are growing in this red graph. A base less than 1, we are decaying in this black graph. black graph, but keep in mind, if our exponent is made negative, that's really the same thing as flipping our fraction. So these two are now the same equation. All right. So that's an example of some of these equations or some of these functions. Let's take a look at how we would solve some equations now. So those were exponential functions and what they look like. You definitely want to play around with your exponential functions, plug in x is 1, x is 0, and x is -1 to just get a handle on what's going to happen. And if you have horizontal or vertical shifts, then shift the points that you plug in accordingly. So now let's talk about solving equations. If we want to solve exponential equations, this is not a function. This is just an equation in a single variable that involves a variable in the exponent. Okay. There's two ways to solve exponential equations. One is to use logs. Logs are the inverses of exponents. We'll talk about those in a minute. The other method only works if we can use the one-to-one property. The one-to-one property basically tells us that if we have two exponential statements equal to each other, and the base of those exponents is the same, then the exponents must be the same. Okay. So in order to use this property, if we can rewrite our exponential equation as one thing to a power is equal to that same base to another power, then we can just equate the two powers. We're not always able to rewrite values as exponents to the same base, but when we can use this one-to-one property. So let's do our first example here, which is this 8 equals 2 to the 2x minus 1. In order to use this property here, we have to rewrite 8 as 2 to some power. Well, 8 happens to be 2 to the third power. So we can rewrite 8 as 2 to the third power. Now our equation says that 2 to the third equals 2 to the 2x minus 1. By this one-to-one property, we can now just equate the exponents and say that 3 equals 2x minus 1. And we can solve that equation to get that x is 2. You can plug in x is 2 back into our original equation, right? If x is 2, this is 4 minus 1 is 3. And in fact, 8 equals 2 to the third, right? So you can always check your answer here. That's how we use the one-to-one property. The first and trickiest step is rewriting one part of your equation as the same base as the other part of your equation. Let's do the second example. 1/3 to the negative x equals 27. So what we need to do here, we can approach this in a couple of ways. Directly, we want to rewrite 27 as 1/3 to some power. Well, 27 is the same thing as 1/3 to the negative third power. Once we rewrite like that, we can equate the negative x to the negative 3, and we get that x is 3. You might ask, how am I supposed to know that 27 is the same thing as 1/3 to the negative 3? You might not understand that. So you can look at the 1/3 to the negative x and say, hey, I can rewrite this as 3 to the positive x, right? Remember how negative exponents work? It's the same thing as 3 to the positive x here. So if we rewrite that as 3 to the positive x, then we get that 3 to the positive x equals 27. And we know that 27 is 3 times 3 times 3. So we can rewrite 27 as 3 to the third. And then we can equate our exponents now that we have the same base and say that x equals 3. So that is solving exponential equations using the one-to-one property. It only works if we can rewrite part of our equation as an exponent to the same base. If we can't do that, then we're going to have to use logs, and we're going to learn that in a later section.